and appreciate that this presentation is quite different from what we have seen before, going into the heart of biomedical instrumentation and measurement science. What I wanted to present is the progress that is being done in the field of biomedical photoacoustics when it comes down to endoscopy imaging for atherosclerosis cases where essentially you'll be looking at patients who may or may not be risky to operate on on an open heart basis, and you want to assess whether or not the coronary artery is damaged enough so that one would justify an operation, as opposed to just simply doing other using other methodologies to contain the disease. So what I will be presenting here is looking at the essence of atherosclerosis. It's a disease that basically strikes a large number of people around the world. This chronic cardiovascular disease is characterized by inflammation and a buildup of lipid-rich plaque. And you can see here, over time, the plaque builds up. The picture on the right-hand side, it builds up so that it could eventually block the flow of blood through the coronary artery, and it could lead to things like heart attack and stroke. So the other aspect is that even if it hasn't happened yet, however, there is what we call plaque vulnerability, which is highly correlated with the lipid composition of the plaque. And then you can see here the plaque in the middle, where it could actually break off and cause a heart attack or stroke. So we have been looking at technologies that exist in assessing the state of the coronary artery vis-a-vis that plaque vulnerability. So what the major technologies to date are, as I show here, first of all, X-ray angiography. This one detects stenosis, the narrowing of the lumen. However, it requires a radio-opaque contrast agent, and it is invasive. It also uses ionizing radiation. So that's something that you cannot take on for too long a time. So there is an issue there that has to be addressed. However, it is essentially the golden standard of today's surgery. On the other hand, you have magnetic resonance imaging, and that is practical. However, it has issues. That is, you cannot use it with patients with metal inclusions, and there are very severe motion artifacts due to the prolonged acquisition time of the signal. So that basically says that maybe you should be looking for some other techniques. Techniques that have a higher contrast now are coming in almost invariably being in the optical range. So here you have a virtual histology, intravascular ultrasound, IVUS, in the middle. And it looks at ultrasound as being a major technology to identify the geometry that exists around the walls of a coronary artery. However, ultrasound is basically a mechanical wave. It's reflected off surfaces that have different density and speed of sound. So as a result, it does not have a high degree of contrast. So, and the resolution, of course, is something that is not all that great with it. However, it has high penetration depth, and that's something that we should keep in mind. Another technique is optical coherence tomography. This one is essentially an interferometric method. Think about a Michelson interferometer, and it's optical. It's high definition. You can actually see nice images. However, it doesn't have high spatial resolution because it does not have a high penetration depth. So as a result, it is something that could be used. It starts to be used now in coronary disease assessment, but it is going to have limitations on the tissue penetration depth. And obviously, one of the other ones less frequently used is positron emission tomography. So that requires an injection of radio tracers again, and therefore it is invasive. So among all, there has been a big effort around the world to generate new techniques to image the insides of a coronary artery. The technique I'll be talking to you about is one I have been involved in for a number of years, which is the ForAcoustic technique. Now, this methodology is actually a very happy compromise, a marriage between optics and ultrasound. So as you can see here, we have if you were to use optical imaging for inspecting tissue, what you're going to find is that you have limitations over a low penetration depth. However, the contrast is very high because this molecular contrast, the particular wavelength that you're using, has different absorption properties for different components of the tissue. So as a result, you can have a high contrast but low penetration depth. On the other hand, you have ultrasound. The ultrasound contrast is low for reasons that I talked to you about before. That is because it's a mechanical wave, so it doesn't have much contrast. However, it has a high penetration depth. So the marriage of the two, that is having the light penetrate the tissue, convert into ultrasound, is something that has been found to be of profound advantage over other methodologies that I showed you before. So here is a case. What happens in the physics of the phenomenon? You have a light absorption. Here's an optical source, a laser. Then the light is penetrating into the tissue and it is absorbed by a component of the tissue. Maybe it is blood, maybe it is a lipid, maybe it is something else. But once you have light absorption, then you have a conversion to heat. So I have a temperature rise. Once the temperature rises, the material undergoes the thermoelastic expansion, which in turn generates ultrasonic waves. And those ultrasonic waves are monitored by piezoelectric transducer detector. So what I'm showing here in this cartoon is basically the functionality of the photoacoustic effect. So also importantly, we have the technology that, because ultrasound imaging has been around for many, many years in the field of biomedical diagnostics. So we already have the tools to generate and detect ultrasound. And that means that in general, you're looking for systems to generate the optical source that will be eventually detected by a conventional ultrasonic detector. The way the field has been developing, it has been in two ways. One of them is a pulse-based intravascular for acoustics. So what you have is a pulse laser, maybe in the 532 to 1064 nanometer, typically a neodymium YAG laser. The pulse duration is about 5 to 20 nanoseconds, and then it strikes the surface of the tissue. It propagates in the tissue, gets absorbed by the medium that you're interested in. That mu sub A is the absorption coefficient, which now generates acoustic waves, and these are the wavefronts of the acoustic waves in the forward and in the reverse direction. And then finally, you have an ultrasonic transducer, either in transmission or in backscattering, and a digital signal processor that is going to pick up the signal and analyze it. So in some ways, it's a very straightforward methodology, because the laser strikes the tissue, and then you have, this is essentially instantaneous because the speed of light is so high. And then you have the acoustic wave propagating as a delayed kind of response, where the distance is equal simply to the speed of sound times the time of travel. So you can tell how deep you really, your signal is coming from. On the other hand, we have another methodology for acoustic methodology. I mentioned the pulse laser system. Now I'm presenting to you the continuous wave laser-based intravascular for acoustic signal processing. These are multi-frequency waveforms for depth-sensitive imaging, and you need to have multi-frequency so that you can get the depth. The more frequencies you have, you can think of a pulse, and a pulse is the agglomeration of a number of frequencies. So you cannot just have a single frequency, because you don't really know, you don't have any depth resolution. So what we have generated, I mean, in the history of technology, is radars. So a radar is basically that. It's one that generates a multi-frequency signal. And here is a signal that has multi-frequencies, this black array here. And the response is also multi-frequency, because whatever frequency you're putting in, you're picking up a signal from that frequency. And the way this operates is what you do in this, you're adopting radar principles in the photoacoustic imaging of tissues. This is really the novelty here. And you can see what the output signal is going to look like, the B of T, which has actually it's a correlation, it's a cross correlation between the incident signal that is the reference, S sub R, and the response of the medium. So if you look on the right-hand side here, what I have is the photoacoustic signal that the reference, first of all, goes in. But because in the time domain, you have integrals to deal with, and integrals take time to be calculated by the computer, then what do? We convert by using the fast Fourier transformation, we convert to the frequency domain. So the frequency domain, in whatever you have as an integral in the time domain, that becomes a product in the frequency domain. So processing products of signals is much faster than processing integrals. And this is the reason why I convert to the frequency domain. At the same time, you want to have a high signal to noise ratio. So what happens is this reference becomes essentially a filter. That you take the fast Fourier transform and you take the complex conjugate of that. So it's a complex conjugate of a delayed version of the incident wave that generates the highest signal to noise ratio in response, because the response is going to be this. There's going to be for acoustic signal and noise. Of course, you have it's in the frequency domain. So you eventually are going to take that frequency domain signal. It is multiplied, here it is X, it's multiplied by the reference, by the delayed version of the complex conjugate of the reference, which gives you a very high signal to noise ratio, comparable to the pulse laser. And then what you have here is a product in the frequency domain. You use an ultrasonic filter too to apodize signals, because there are extraneous frequencies due to noise. You can filter that signal. And then eventually you use an inverse Fourier transformation to get an output signal, because you still want to be in the time domain. So you started with the time domain, went into the frequency to speed up the process, and then back in the time domain. So what you're going to get is an amplitude and a phase, because these are complex signals. And I'm showing here the fact that one of the things that we discovered with this is that once you multiply the amplitude by the phase, by the inverse of the phase, then you can get a much better output. And this is a case in the bottom here. This is where the amplitude response is supposed to be. The signal to noise ratio, 59 dB, and the full width at half maximum, 0.31 microseconds. But then once you use the phase filtered amplitude, that is, you multiply the amplitude by the inverse of the standard deviation of the phase, the signal to noise ratio becomes a lot higher, and the full width becomes even narrower, because the phase is more narrow than the amplitude. So you get a much more accurate signal that way. And I'm showing you here what the radar has been doing, what we know radar for in the past. And we know it by actually having a signal, an electromagnetic signal, basically hit the target. In this case, it's an airplane, and you're looking at the response back of the plane. So in the control tower at an airport, people can actually tell where the plane is at any given instant. We're using the same kind of approach in the frequency domain. So if you look at the overview of these two modes of intravascular for acoustics, what we have is in the pulse excitation, the advantages are high power nanosecond long pulses, a broadband response. These are very narrow spikes, optical spikes. So they have a very, in the Fourier sense, have a very wide frequency response. Therefore, you have a broadband detection. You can see signals at very fast times and at slower times. However, the sources that you use are pulse lasers. They're expensive and bulky. There is a strong acoustic transient because you have a confinement of the optical signal in the medium, and you get a straightforward time domain processing. The disadvantage is that this is acting like an optical hammer, so you have no opportunity to change the parameters of the system. Whatever the laser wants to do, the laser does. So your processing is simple, but you cannot optimize a signal by um, uh, adopting it to the adapting it to the response of the transducer and the other parameters of the system. On the other hand, in the frequency domain, what we call frequency swept continuous wave optical excitation, the radar that I mentioned before, you have a low power continuous irradiance, a more narrow band response because the frequency modulation is within a certain amount of time, range of frequencies, and a narrow band detection. However, great advantage, the source is cost efficient and compact. These are small semiconductor diodes, so you can make portable systems out of that. You have a weak acoustic transient as opposed to the strong transient that you have with a pulse laser, but in the frequency domain processing, you have a lot of tools that you can use so that you can increase the signal to noise ratio, you can put filters, you have flexibility in optimizing system parameters and using what we call waveform engineering. So there are advantages to both of these systems, and I just wanted to present to you what these advantages are for each one of them. We opted to develop the frequency domain system, which is what I'm going to, because many other people are using the pulse system. However, appreciating the advantages of frequency domain, we decided years ago to go in that direction. And one of the important advantages is that we can use a market or a commercial kind of ultrasonic imager. This is an ultrasonic imager that's marketed by Sonics Touch. This is a biomedical ultrasonics imager that you can use in a hospital, and it basically has a LCD displays and touch screen, transducer holders, all sorts of different things, and so that you actually have your transducers right there, ready for your use. And then you have the Sonics Touch, this blue box, and the blue box is a Sonics DAC add-on. It is a system that allows the ability to introduce extra commands to the imager. And that's very important because it is through this interface that you can introduce the laser parameters and pick up the photoacoustic response. So the advantage of using this kind of an imager and using the frequency domain is because for these commercial medical imagers, the frequency domain is being used. There is actually a frequency signal that goes out by the ultrasonic transducer to the patient, and then this picks the transducer picks and the system picks up the response back from the patient. So this is already in the frequency domain. It's just like the frequency pulse is lasting for a certain amount of time, and then it's cut off. So you have the pitch catch kind of a system of a signal generation and response. And then what you're doing is you can add the laser also in the frequency domain, so it recognizes those frequency signals. The software does not need a great change from what it already is. So you can look at the last line here where I said achieving PA imaging functionality on a commercial ultrasonic instrument could accelerate clinical acceptance and use. So why reinvent it if it's already there? Just put the laser on, tweak the software, and see if you can have a good imager. Now, when we're applying this to catheters, you remember we need to go to the coronary artery, so we need to have a catheter in there that will be able to image the walls of the artery. So I'm showing some conventional for acoustic designs for the coronary artery. And then what we're seeing is almost all of them, they have torque cables because you really need to rotate around. Here is, maybe I could show you the undersea. You can see here that there is the light going in down to the to the surface that it's supposed to monitor, and then the ultrasonic signal that comes out of that surface is going back onto this catheter, onto the tube, and to the outside world. So you do have to have an optical fiber to bring the light in, and then the ultrasonic transducer is picking up the signal with a wire and takes it to the outside world. Of course, this has to rotate, so it's rotating around 360 degrees to be able to image the one plane over the entirety of the wall, and then it is pulled back. And you can see here some of those, they have this torque cables that are allowing them, the torque coil that allows them to move out as it's rotating. So eventually you'll end up with a three-dimensional cylindrical image. This is what these catheters have in common. Now, what are we looking at? What is the signal generated from? Well, here is a spectrum on the upper left-hand side of a tissue, a human atherosclerotic artery in the near infrared spectral region, and it has two components. One of them is at 1210 nanometers. There's an absorption peak here for the lipids. These are the lipids that form these vulnerable plaques that are important to identify because they could be causing a stroke and eventually death to a patient. But on the other hand, you don't only have the lipid, but you also have all sorts of other things here. There's water, elastin, collagen. These are typical sort of biochemicals of the tissue, of the walls of the artery that have to be there, and they do absorb. So if you look at those, though, they generate a pretty much more or less slightly change in baseline. And the issue about this is that the major change is that for water. And water is always standard because water absorption increases as you go into the infrared. So what we have done here is we introduce a system that not only does it monitor the plaque at 1210 nanometers, but also automatically subtracts the absorption baseline of the other surrounding elements, such as elastin and collagen in the system. And those could be quite variable from one patient to the other. So you don't really know what they are. You cannot kind of account for them by calibrating ahead of time. That's why this differential or wavelength modulated ForAcoustic radar was introduced. And what you really see here is how it operates. That is, we have two lasers, and one laser is on while the other one is off. So when laser A, which is monitoring the absorption of the lipid, is on, then the laser B is off. So here's the acoustic signal from laser A going up. Here's the acoustic signal from laser B going down. So they're opposite. They're operating 180 degrees out of each other. So the signals are automatically subtracting from each other. And you're getting pretty much a good quantitative idea of what the height of the peak, of the lipid peak is, which is what you'd like to have. You'd like to have a quantitative spectroscopy, quantitative imaging of how much plaque you have on the wall of the artery. This is how this thing is working. So you can actually zero the two signals beforehand, before you go into the lipid, so that you will know that you have essentially an equal strength of signal without the lipid in the system. And that's something that could be monitored, and it could be tabled ahead of time so that you have registered the baseline into your system. But in reality, you're always looking at the differential signals between the two. The system basically looks like this. You have a catheter. In the catheter, you have a fiber optic medium. There is a mirror here, and the mirror is shooting the laser light onto the region of interest. And then you have the transducer that is picking up the acoustic wave coming out. This is a picture of what a transducer looks like. It is typically a 1 millimeter by 1 millimeter transducer in the megahertz range. And you can see here you have the two lasers, the driver of the laser at 1210 nanometers and the driver of the laser at 980 nanometers. So they're operating 180 degrees out of phase in the system. Now, we're showing here that we tried this with two different kinds of samples. One of them is phantoms of an atherosclerotic artery. We used the pig artery with cholesterol lumps. There are 4 lumps, 1, 2, 3, 4. One of the things that we find is that the 2 lumps, 1 and 3, are quite large and visually distinct from each other. We can see them right here, but then lumps 2 and 4 are not. So they're small and they are not visible, certainly. So we wanted to see what the extent of the sensitivity of this kind of sensing is going to be. Now, in ultrasonic systems, the wavelength of the ultrasound determines also the degree of the resolution. So you really need to have high frequencies. How high could they be? Well, there are some issues here. We use the low frequency, which means 1 to 5 megahertz. And then we also use the high frequency, 3 to 24 megahertz. The main limitations here are the driver of the laser, because these laser diodes could be driven. But in order for them to be driven, that means that they have to see a sine wave coming in to sort of operate the laser in the modulated mode. However, the interface between the driver and the laser is acting essentially as an inertia, as a reluctance. So if you do not have a very good engineering at the interface, you're going to find out that the high modulation frequencies are basically attenuated. So you're converting your signal into the DC instead of having an AC signal going in to generate a modulated laser beam. So to this point, the state of the technology in the world is that you can do up to maybe 30 megahertz, and we look into the possibility of 40 megahertz as it stands right now. But this is our next step. So these are some of the results that you get to see the difference between in the atherosclerotic pig artery, to see the difference between pure ultrasound, which is what you would do if you went to a clinic and you had an ultrasonic imaging of your coronary artery. You see here, you have the lipids, but they don't really register because you can see them there, but only after you have seen the photoacoustic signal, because here I have a true contrast. Here it is molecular contrast generated by the wavelength of the light, whereas in the ultrasonic image, all I have is the mechanical contrast of the interface. And this is exactly what the ForAcoustics adds to the ultrasound. So typically what we do is you have the ultrasonic image. That's very important because it sets a stage for what the surroundings are. What are the surroundings of your image? Ultrasound is extremely good at doing that. And then inside those surroundings, what are the absorbers that you're really looking for? That is what the ForAcoustic part of that does. So it is a happy marriage, I suppose, made in heaven or made in the surgery, but that's exactly what you're looking for. So then the other aspect is go now to human atherosclerotic case, where we have a cadaver and we have atherosclerosis, and you can see here, after you open up the coronary artery, you can see the degree of atherosclerosis on the walls. Once you go up to high frequencies, you have an issue with these signals. That is, you have radio frequency components coming in because the current that is communicated to the laser is essentially acting as an antenna. So it is outputting signals that are seen by the detector, and those signals have to be taken out because otherwise you'll be having erroneous signals due to the radio frequency. And also the wall is generating a signal because you're just simply bumping your energy against the wall, but you really want to look at the absorber that is at the lipid on the wall. So what we're doing here, we normalize the photoacoustic amplitude from plaque. So you can see here in the bottom that we have the baseline. The radio frequency, of course, is out there, but then I have the plaque and the wall. So the radio frequency and the wall. So these are the signals that are normalized out so that I can ultimately see the peak due to the lipid. This is the peak that I'm really looking for. So you're looking at 1210 alone. If I had only one laser, I'd also be seeing these other contributions that are not real. If you look at the 980 nanometer alone, I'd be seeing those other contributions that are there, but they are not part of my lipid. So once I have the differential signal, now I'm seeing the difference between the two. And again, this is the amplitude speaking, but remember, we get a much higher signal to noise ratio if we take the amplitude and multiply it by the inverse of the standard deviation of the phase. And the reason for that is because, and this is the last trace right here, the PFA, because the phase has a narrower bandwidth, so it gives you a higher spatial resolution. And once the signal goes out of lock, the phase is almost digital. It either locks if there is absorption, or it's totally unlocked if there is no absorption. So the standard deviation is all over the map, which actually looks like it's wild signals up and down. If you divide by a large signal, then you get essentially a zero. And that's why it is the inverse of the standard deviation. So this is a nice way of getting signals. And what I'm showing here is a low frequency for acoustic imaging. Remember, we use the low frequency transducers. This is the ultrasound. The ultrasound, again, it's a mechanical wave. The absorbers are there, but they're optical absorbers. You don't really see them very well in the ultrasound. However, if you use the ultrasound and the differential for acoustic amplitude without going through the phase normalization, I'm already seeing those absorbers, the position of those lipids inside the artery, and I see them right here. And then, in addition to that, we're also doing the inverse phase filtering, which is going to make them more precise, at least locally. You have to look at them locally. So this is what it means by looking at them locally. You have the ultrasound here. You have the ultrasound at the differential for acoustic amplitude. The A, B, C, D, all the way up to G, all of them correspond to the locations of the lipids. For instance, you look at F down here, this is what the lipid is, and I'm looking at F, this is exactly what the lipid is. This is without the phase filtering, this is with phase filtering, and you can see that this becomes more spatially resolved once you put phase filtering. For sure, it is much better than the ultrasound alone, but then this becomes more spatially resolved. And again, this is actually quite nice because we're only using up to 4 megahertz of sound. So usually in cardiology, in clinical practice, the ultrasonic transducer is up to 40 megahertz in order to be able to see this kind of resolution. But the light, the resolution that you get from the light and the confinement of the absorber, it's almost as if you had a higher frequency transducer operating under this lower frequency instrumentation, which is absolutely marvelous because this is exactly where we want to be. And now I'm showing to you essentially what the low versus high frequency responses are. Here on top, I'm showing again the artery from the cadaver, and then the first row here shows the ultrasonic signal versus the low frequency differential for acoustic amplitude versus the low frequency differential for acoustic amplitude with the phase filtering. There's not a whole lot of difference because, again, it's low frequency and you get a certain amount of spreading. I mean, the acoustic wave is still spreading sideways, so it tends a bit to mix the regions, the local regions that have response versus those that do not have a response. However, it gets better once you go to the high frequency, the 14 megahertz transducer, because here you look at the differential amplitude at the higher frequency to be compared, I suppose, with the one at the low frequency on the left, and then you look at it under the PFA. So now we're seeing a fair bit more structure inside the lipid once the phase has come in as a filter. This is one example, and then this is plaque C, and then we're looking at plaque E as well. So plaque E is the ultrasonic signal. Very little to be seen here. I will not be able to tell that there is a plaque. And then the low frequency differential amplitude, again, once it is filtered by the phase, it makes some difference, but not a whole lot, because in both cases the wavelength is still long enough so that you kind of smear around the adjacent structures. On the other hand, once you go to the high frequency, you see much more detail on the differential amplitude and even more detail on the phase, where you can see the true regions that are full of lipid, and they're surrounded by other regions that have lower amounts of lipid than the full region. Okay, so then, having presented to you the advantages of the frequency domain for acoustic imaging in cardiology, I'm coming up with my conclusions, which is what I presented to you. So we introduced frequency domain modality to endoscopy imaging in arteries that we found have the following characteristics. They provide independent imaging channels, amplitude and phase. That's very important because that's something that I did not mention before, that the phase is laser fluence independent. That's very important in biomedical imaging, because where the light is coming from is not a simple pathway. I don't see the ForAcoustic signal coming in from a particular depth, but as there are overlying structures, those structures are also adding to the signal. So, and also importantly, because they are there, they sometimes prevent the laser light to go to the lower regions. So the intensity of the light that reaches a region below something else is different, is less than the intensity of the light somewhere else in another region of that I'm scanning. So the outcome of that is laser fluence dependent, and this is what the amplitude does. But the phase is a ratio of two signals. It is, because it is a frequency domain wave, it is the quadrature of the wave versus the in phase. This is what we all learned in introductory physics, that I have an amplitude and a phase. But because it is a ratio, the laser fluence cancels out. So the phase is the true ultrasonic, the true ForAcoustic signal, which is less sensitive than, or even insensitive to, the laser fluence. That is a very important issue. In other words, with the two images that I get, the amplitude and the phase, I will believe the phase more than I'll believe the amplitude, even though in reality I need both of them. Now, it is amenable to frequency domain spectral filtering optimization through appropriate waveform engineering. And this is what I said to you. Pulse laser is a hammer. There's not much you can do. With the frequency domain, you have a smaller signal, but you have to do signal processing and waveform engineering in order to be able to get things out, to optimize, for instance, the range of your transducer response with the appropriate range of frequencies. There's all sorts of things you can do to optimize the signal. The wavelength modulated differential ForAcoustic radar is not affected by signal interferences such as radio frequency, because you can normalize those out and therefore can get the true response, imaging response of the system out of that. Now, when we're co-registering with the ultrasonic imaging, remember, I'm getting an ultrasound and the ForAcoustic signal, both of them one on top of the other. So the co-registration of the two provides a very sensitive and specific endoscopic technology. So right now, our aim is to be able to monitor heart disease, the fact that we start seeing those vulnerable plaques very early in the coronary artery, to warn the patient that we need to do something about it now, when the disease is not fully blown, and therefore the cardiological cardiological response would be good, and you would not have interventions by the hospital, such as open heart surgery and things like that. Much easier to look at very early stages of arterial disease. Now, of course, the advantage of the pulse laser is I can get 40 megahertz, which is what the commercial transducers are in cardiology, and especially in the coronary artery response. But what we've shown here is, because of the optical response of the system, even in the frequency range from 4 to 14 megahertz, we're able to see the size of the plaque, very small size of the plaque, because we're really looking at optical absorption as opposed to purely ultrasonic dispersion, which is long wavelengths, smearing of the feature, and not being able to look at a good spatial resolution. So the the light allows us to increase the spatial resolution compared to the ultrasound. So finally, what we're aiming at is to of course, you have a radio resolution that is improved when we combine both the amplitude and the phase images in one, as I showed to you before. And the catheter miniaturization is basically what we're planning to do. That is, our next goal here is to make this even smaller. We have 1.5 millimeter transducers. We need to go down to less than 1 millimeter, maybe 800 micron transducers to be able to get inside the coronary artery, whose internal diameter is about 1 millimeter. So we're working in that direction as the next phase before we can get into the clinical stage. So having said that, I wish to thank you for your attention and my presentation here. In my last slide, I'm showing the agencies that have funded the research, and at the same time, I'm also showing my contact in case that somebody's interested in the work that we do and they wish to pursue it further. Thank you very much.